My name is Muriel.
I'm Air.
I'm Kim.
We're back.
A transportation problem deals with the distribution of goods from several points of supply, origin, or sources to a number of points of demand or destination. Finding the best way to distribute goods, usually by finding the least cost, is the objective of a transportation problem. There are 4 steps in solving a transportation problem. Number 1, balance total supply and total demand. Number 2, identify if it's a minimization or maximization case. Number 3, solve using one method. Number 4, compute the total transportation cost. There are 2 ways to balance a transportation matrix. Number 1, if demand is greater than supply, add a dummy column containing 0 cell value and the corresponding demand value. If the demand is less than supply, add a dummy row containing 0 cell value and the corresponding supply value. Usually, a transportation problem is a minimization case because its objective is to find the least transportation cost. But in the case of a maximization problem, where cell values are larger numbers, you find the biggest or largest value in the cells and subtract this to each cell value to convert the matrix into a minimization case. We will introduce you to 3 methods in solving a transportation problem. Number 1, Northwest Corner Method or NWC method. Start from the upper left corner of the matrix and exhaust the least value in either the supply or demand and proceed to the next upper left corner of the matrix, then repeat the steps until all supply and demand are exhausted. Number 2, Minimum Cell Cost Method or MCC method starts with the smallest cell value and exhausts with the least value in either the supply or demand, and then proceed to the next smallest cell value and repeat the steps until all supply and demand are exhausted. Lastly is Vogel's approximation method, or VAM. Calculate the difference between 2 least cost cells for each row and column, then select the largest difference. In case of a tie, choose the one where the maximum quantity can be assigned. Exhaust the least value in either the supply or demand, and repeat the steps until all the supply and demand are exhausted. To compute for the transportation cost, it is simply the summation of the products of sources and destination.
The company manufactures office desks at 3 locations: Des Moines, Evansville, and Fort Lauderdale. The firm distributes the desks through regional warehouses located in Albuquerque, Boston, and Cleveland. An estimate of the monthly production capacity at each factory, the monthly demand at each warehouse, and the shipping cost per unit from each factory to each warehouse is shown in the table. We see in the table that the total factory supply available is exactly equal to the total warehouse demand. When this situation is equal demand and supply occurs, a balance problem is said to exist. We can now use the Northwest Corner rule to find an initial feasible solution to the Executive Furniture Corporation problem shown in the table. Beginning the upper left-hand corner, we assign 100 units from Des Moines to Albuquerque. This exhausts the capacity or supply at the Des Moines factory, but it still leaves the warehouse at Albuquerque 200 desks short. Move down to the second row in the same column. Assign 200 units from Evansville to Albuquerque. This meets Albuquerque's demand for a total of 300 desks. The Evansville factory has 100 units remaining, so we move to the right to the next column of the second row. Next, assign 100 units from Evansville to Boston. The Evansville supply has now been exhausted, but Boston's warehouse is still short by 100 desks. At this point, we move down vertically in the Boston column to the next row. Assign 100 units from Fort Lauderdale to Boston. This shipment will fulfill Boston's demand for a total of 200 units. We note, though, that the Fort Lauderdale factory still has 200 units available that have not been shipped. Lastly, assign 200 units from Fort Lauderdale to Cleveland. This final move exhausts Cleveland's demand and Fort Lauderdale's supply. This always happens with a balance problem. The initial shipment schedule is now complete. We can easily compute the cost of this shipping assignment. From route D to A, 100 units has been shipped, multiplied by 5 per unit cost, equal to 500 total cost. Next is, from route E to A, 200 units has been shipped, multiplied by 8 per unit cost, equal to 1,600 total cost, and so on and so forth. So the total cost is 4,200. This solution is feasible since demand and supply constraints are all satisfied.
Assignment model or Hungarian model is a class of linear programming problems that involve determining the most efficient assignment of people to projects, salespeople to territories, etc. Its main objective is to minimize the total cost or time performing task at hand. It is a special type of transportation problem in that it provides an efficient means to finding the optimal solution without having to make a direct comparison to every option. In an assignment algorithm, there is a term called opportunity cost, which shows the relative penalties with assigning any person to a project as opposed to making the best or least cost assignment. In this, we have to make assignments such that the opportunity cost for each assignment is 0. In an assignment matrix, there are rows, which are objects or people we want to assign, and columns are the tasks or things we want them assigned to. The goal is to assign projects to people so that total costs are minimized, since most assignment problems are minimization problems. There are 4 simple steps to a balanced assignment problem. Number 1, row reduction. Number 2, column reduction. Number 3, optimality test. And number 4, total cost. There are 2 types of special cases in an assignment model. The first is an unbalanced assignment problem where the number of tasks, the number of columns does not equal to the number of people or the number of rows. To solve this case is similar to the transportation problem where you make a dummy column if the number of rows are greater or dummy row if the number of columns are greater. In the case of a maximization assignment problem, simply subtract each rating from the largest rating in the table to convert to minimization. We shall now proceed to an example problem. Miss Chi wants to assign her students to an out-of-school activity where 5 groups are formed to go to a mall in Cebu. The group leaders will rate each location they want to be assigned with a scale of 1, less desired, to 5, most desired. Which assignment should be made if the total of the ratings is to be maximized? Since it is a maximization case, we will subtract the highest value with the other numbers in the cell. In this case is 5. This is then converted to a minimization case. The first step is called row reduction. This step is simply the subtraction of all values in one row with the lowest value in that row. For the first row, the lowest value is 0. Thus, values will remain the same. Similarly will happen with the second and fourth row. For rows 3 and 5, the smallest value is 1. Thus, all values must be subtracted by 1. Next step is column reduction, similar to row reduction but this time for each column. The only column with no zeros is the fourth column. Subtract all values with the lowest value in that column, which is 1. Third step is the optimality test. Cover all the values in a row or column wherein most zeros are covered with minimum lines. I must emphasize that you must cover the matrix in as less lines as possible. If the number of lines are equal to the number of rows or columns, the matrix is optimal. If not, then repeat steps 1 to 3 again until equal. In this case, it is equal, so the matrix is optimal. The assignment can be determined by the zero opportunity cost or the zero value that correspond to the row and column that zero value is in. Encircled here are the possible assignments. Write down your answer and compute for the total rating. After a few seconds, check if we have the same answer. The optimal solution is as follows. And the total rating is 22.
And that's all for today. We hope we help you with our discussion.
Tune in next time for more lessons on operations research.
This is Mac. See you next time. Bye.